Okay, well, good afternoon, everyone. I want to welcome you to the 11th Annual Shannon Memorial Lecture. Let's see, I guess I'd like a slide to appear on the screen. Thank you very much. So I'm very pleased to have Professor Abbas Al-Gamal from Stanford University as our speaker this year. He's the Hitachi America Professor in the School of Engineering and belongs to the Department of Electrical Engineering, where he is currently serving as chair and speculating about his future in that role. He also is the 2012 Claude Shannon Award winner. So this, as you know, is the highest award given by the IEEE Information Theory Society. Today he's going to speak about networks with point-to-point codes. For those of you who aren't familiar with the origins of this lecture series, it began in 2003 and is supported by an endowment that was established by Professor Jack Wolf. So I think I want to just thank him again. It's been a very successful series. So as I said, this is the 11th, so I thought I would show the speakers from the first decade of this series, and some of you may recognize the names of the distinguished speakers. You'll see in year 5 we actually had 4 speakers, all who had recently won awards and from the Information Theory Society and the Communication Theory Society, and you'll recognize a couple of familiar names from UCSD up there. So now we are into the second decade. Okay, you get the idea. So we're very interested in having Abbas begin the next decade for us. I thought I'd spend a few minutes giving you some background on him. So he has broad interests and has made contributions in a very wide variety of areas, including network information theory, which may be how most of you know of his work, but also the design of FPGAs and digital imaging. He had his graduate education at Stanford in statistics and electrical engineering, and has been on the faculty there as a professor of one rank or another since 1981. He was the PI for a well-known program there having to do with programmable digital cameras, and some of that work actually ended up getting spun off into companies that I'll mention shortly. He also was the director of Stanford's well-known Information Systems Laboratory, ISL, for 5 years. He's very active in the Information Theory Society, especially of late. He's been on the Board of Governors since 2009, and he's currently the first vice president of the society, which means that next year he'll become the president of the society, because that's how it works. He has over 200 papers and 35 plus patents. As I said, many of you will be familiar with his work in network information theory, including his recently published book, which is really a beautiful text that he co-authored with our very own Young-Han Kim. Young-Han isn't here, by the way, because he's on sabbatical in Korea, but he a prestigious award, the so-called Prose Awards. Last year it was selected for honorable mention in the field of engineering and technology, and I hope that that award is for you, Abbas. So Abbas has many well-known papers in all of the areas that I mentioned that are highly cited. I thought I would just mention one here, which is one of his early smash hits with Tom Cover, his paper Capacity Theorems for the Relay Channel from 1979, has, according to Google Scholar, almost 3,000 citations. He's won numerous awards. He was elected an IEEE Fellow in 2000 for pioneering applications of probability and statistics to develop new methods for the analysis and design of integrated circuits. He won the 2004 Infocom Paper Award for the paper Throughput Delay Trade-off in Wireless Networks. And as I mentioned, he was the recipient of the IEEE Information Theory Society's Claude E. Shannon Award last year. And just this year, he was elected to the National Academy of Engineering for his variety of contributions in information theory, information technology, and image sensors. So here are some of Abbas's companies. So in 1984, he was in charge of the LSI Logic Research Lab, which became their consumer product division. They're still around, doing quite well. In 1986, he founded Actel, which has now become Microsemi. 1990, he started Silicon Architects, that was acquired by Synopsys. And in 1999, he started a project that was a spin-off of that work on digital cameras, founded Pixum, which I just actually learned at lunch today, had been acquired by Sony recently. And I love that little subtitle there, every pixel tells a story. So now I want to start the actual lecture. But I thought that to convey my level of excitement and enthusiasm, I would harken back to an expression that is familiar to me from my youth. It may date me a little bit, but I also, as part of this, give a nod to the ITA head transplanting on their poster from the spring or February. Yabba-dabba-doo! So, Yabba Dabba Abbas, please join me in welcoming our Shannon Memorial Lecturer.
So is he gonna switch the... Is he gonna switch? Yeah. Oh, okay. Oops. Okay, good afternoon. Thank you very much, Paul, for this very long and nice introduction. It's looked like my life story, kind of. So I feel very honored that I'm giving the Shannon Memorial Lecture today. And what makes this event even more special for me is that it's at UCSD, which is my second most favorite university, for several reasons, actually. The first reason is that a long time ago, Alon Orlitsky was an early student of mine, and of course, he's now one of the leaders of our society. And in the last 5 years, I spent many weeks and hours and days, both physically and virtually, at UCSD, working with Young Han Kim on our book. And this was, to me, this was one of the most fruitful collaborations, research collaborations I've ever had. And during that time, I met many faculty at UCSD and students and postdocs, and made many friends here, and they always made me feel at home when I was visiting. Last but not least, my middle son studies at Scripps, a PhD, is doing a PhD at Scripps, so I would never miss a chance to come to UCSD for whatever reason. And of course, this is one of the best reasons. Okay, so my talk today will be about how well point-to-point codes perform over networks. Okay, so in his 1948 magnum opus, Shannon says, the fundamental problem of communication is that of reproducing at one point either exactly or approximately a message selected at another point. Shannon considered a point-to-point communication system in which a sender wishes to send a message which is randomly selected from 1 to 2 to the NR messages and send it over to a receiver over a discrete memoryless channel so that the receiver can recover it with high reliability. So to achieve this goal, you use an encoder that maps the message into a code word of length n transmissions, and then the decoder, upon observing the received sequence yn, reproduces the estimate m hat. To measure performance, Shannon used the probability of error. And to determine the ultimate performance limit or information flow on for this setting without any constraints of coding complexity of block length, he used an asymptotic approach. He defined, he says that the rate R is achievable if there exists a sequence of codes such that the limit of the probability of error goes to 0, and then defined the limit on information flow, which he called the channel capacity, as the supremum of all achievable rates. As you all know, of course, Shannon found a beautiful formula for the capacity of the discrete memoryless channel as the maximum over probability mass functions on the input x of the mutual information between the input x and the output y. And Shannon realized that trying to actually construct codes that achieve the capacity can be extremely hard and maybe not even doable. And so he gave an existential proof of achievability via random coding. So you fix a probability mass function on x, p of x, and then you randomly generate 2 to the nr sequences independent of each other, each according to the product using p of x. And that would be the code book that would be shared between the sender and the receiver. From now on, when I mention the word random point-to-point code, I mean exactly this. I mean it's a code that is generated from some fixed probability mass function on some alphabet and generated independent of each other, and each is according to the product distribution. So this is what I mean when I say random point-to-point code. I'm also going to refer to the notion of a random code book, which is basically the set of random sequences from which the code is drawn. Okay. So here, in this picture here, I have the code words in xn space that were randomly selected. So encoding is very straightforward. To send a message, the encoder transmits the code word from the randomly generated or from the random point-to-point code that was generated, send that over the channel. And decoding, since the messages are equally likely, the optimum decoding rule is simply maximum likelihood. Gallagher and others analyzed the probability of error for the maximum likelihood decoder and showed that the average over the random code book of the probability of error goes to 0 if R is less than the mutual information I of x, y. And as a result, since the average goes to 0, hence good codes do exist. The nice approach about maximum likelihood decoding is that you get quite tight error exponents, tight bounds on the error probability. However, it's difficult to extend the analysis of maximum likelihood to networks. That hasn't been very successful. In fact, this is not the way that Shannon established achievability. He used the suboptimum decoding rule, which is a joint typicality decoding rule. You basically find a unique message such that the code word for m hat for that unique message and the received sequence yn are jointly typical. So in this picture here, you receive yn, you look back and see if there is a unique message for which the code word is jointly typical, then you declare that message to be the message that was sent. Okay? So now there are many ways to define typicality, and one of my favorite ways, because of several reasons that I'm not going to get into, is the one which is called robust typicality by Orlitsky and Roche in 2001. And basically, the definition here is that the empirical joint probability mass function of the sequences xn and yn is close to the p of x and y for every x and y. Okay. So that's just one definition, but there are many other definitions. Now, once you use, the advantage of using joint typicality is it is incredibly straightforward to show that the limit on the expected value of the probability of error over the random codebook goes to 0 if R is less than the mutual information I of x and y. It's maybe two or maybe 3 lines. Okay, so what does that show? This shows that random point-to-point codes achieve capacity, because we can always use the input probability mass function that maximizes the mutual information. A less known fact is the following. You can also prove a converse for random point-to-point codes. So you can make the following statement. You could say, given P of x and a decoding rule, if the limit on the average probability of error over the random code book is to 0, then R must be less than or equal to I of xy. The proof of this result isn't very difficult. And for the point-to-point codes, it shows one interesting thing. It shows that joint typicality decoding achieves the same rate as maximum likelihood. It shows that with maximum likelihood, you cannot do better than with for random point-to-point codes. Well, that's not very surprising because we know how to analyze the performance of maximum likelihood decoder, so we can show it that way as well. And there is a converse for the whole that's even more general than just for point-to-point codes. So, this result is not really that interesting for point-to-point codes, for the point-to-point communication channel. However, a lot of the results that I will mention in my talk rely very heavily on extensions of this very simple converse for the point-to-point codes. When we talk about networks where maximum likelihood is difficult to analyze, and in fact, most of the time we don't even know what the capacity is. So in that case, this extension of this result is really all we can do to evaluate the performance of random point-to-point codes. Okay, so I'll refer to this result later. Okay, so to summarize, there are good codes with rate R less than I of xy. In fact, most randomly generated point-to-point codes with rate R less than I of xy are good. But encoding and decoding them is computationally prohibitive. Very large lookup tables and a lot of searching. And so coding theorists spent over 60 years looking for practical codes that approach capacity and have computationally tractable coding complexity. And in fact, recently, in the last, say, 10 years or so, several such codes have been found, both algebraic and random codes with specific structures. And these codes have been shown to be optimum over certain types of channels. And they are now used very widely in communication networks and storage systems. However, results in network information theory suggest that we need to develop new codes when we to get the most out of networks. Okay, so that motivated my talk. And the question that motivates my talk is, how well do random point-to-point codes perform over networks? Today, everything we know about is point-to-point codes. So are we doing well or are we doing badly? Yeah, I think that's a fair question. If we're doing great, then why bother with network information theory and why bother with anything? We are doing fine, right? If we're not, then what should we be doing? Okay. So do we need to spend another 60+ years looking for practical network codes, or are we doing just fine? So here's a brief outline of my talk. First, I will give a very brief introduction to network information theory, and then discuss, for the rest of the lecture, I will discuss several network models with random point-to-point codes. What we will find is the following. We will find that random point-to-point codes with more sophisticated decoding than what we use today can perform very well. And so in some sense, we're doing fine with the codes, but we're not doing fine with decoding them. We'll also find that joint typicality-based decoding continues to achieve the same rates as the optimum maximum likelihood decoder. But we will also find that there are settings where we may need to develop network codes. Okay. So let me say a few words about network information theory. The work in network information theory aims to extend Shannon's point-to-point information theory to networks with shared resources, with multiple sources and destinations, and shared resources such as multiple access, broadcast, and interference situations, as well as multi-round interactive communication and cooperation via multi-hop. The first paper in this area was by Shannon in 1961. It was on the two-way channel, and he couldn't actually establish the optimum rates for the two-way channel. It turned out to be one of the hardest problems in this area, in fact. And as a result, there wasn't really much follow-up work on this paper. But then there was significant progress in the 70s and early 80s, spurred mainly by Tom Cover's 1972 paper on the broadcast channel, and Slepian and Jack Wolf's 1973 paper on distributed source coding. And here what I have a plot here of the number of papers published in ISIT during this time, and you can see a decent number of papers were being published in network information theory. Now you say, well, 15 papers is not really very much, but the size of the society and the size of the conference during this time was considerably smaller than it is today, and now, so that was a healthy fraction of the number of papers in the conference. But then something happened, and mainly because people got stuck on many problems, and also there was no interest from the practitioners. The field kind of died in the late 80s to the late 90s. There were almost no papers published in ISIT on the subject. And with the advent of the wireless communication internet, revived the interest in the late 90s, and there were, by the early 2000s, there were very large number of papers published in this area. And even though most problems, and even though there is no complete theory for information flow in networks, Young Han and I decided that it's probably time to put together the known result and present them in a simple and unified manner that maybe help future development of the topic, and also serve to people can use it to learn about this subject. Okay, so the rest of my talk, I will talk about various network models with point-to-point codes. There are some redundancy. There is quite a bit of commonality between some of the models I will talk about. However, there are some important differences that would highlight some of the conclusions that I will make. So the first model that I'm going to look at is multiple access channel. This is a model where a two sender, one receiver, multiple access channel. And for example, this could model the uplink of a cellular system. So each sender has a message, and they want to send it over a shared medium like a wireless channel to a common receiver. And we define the problem in more or less the same way that we defined a point-to-point communication channel problem, except now we have a trade-off between the rates of communication of sender 1 and sender 2. Since they share the same medium, if sender 1 sends at a high rate, then sender 2 may have to back off, and vice versa. The limit on information flow in this network is characterized by the capacity region, which is the closure of the set of achievable R1, R2 rates. Alzwede and Liao established the capacity of the multiple access channel a long time ago. They showed that it's the convex hull of the union over product probability mass functions on x1 and x2, which are the two input alphabets, of R of x1, x2, which is this pentagon region. Okay, so now let's see how well random point-to-point codes do over the MAC. So what we do is, for every sender, we generate a point-to-point code. And of course, they are drawn according to P of x1, P of x2, which are independent of each other because there is no cooperation between the senders. And of course, the encoder will simply transmit the code words corresponding to the messages. Okay, so this is just, so now I'm using two random point-to-point codes. Okay, now let's see how well these do. Decoding. So now the first thing we're going to do is to use the same joint typicality decoder while treating the other code word as noise. Okay, so what I'm going to do is I'm going to decode message 1 from y, n, and then decode message 2 from yn, let's say using joint typicality. What can I achieve? I can achieve this point here, which is I of x1y and I of x2y. Achieve, of course, any point in this rectangular area. Can we do better? So this is basically what we do today. We just decode each guy separately. Okay? So now can we do better than that? And the answer is yes, we can do better than that. One way to do better is to do the following. After you recover the first message while assuming the second code word as noise, you can now use the fact that you know, hopefully you decoded it correctly, you can now use the fact that you have that information to do a better job at decoding the second message by finding the jointly typical x1, x2, y, the unique jointly typical m2 hat with x1, m1 hat, and y instead of just with y. Okay? So with that, you can achieve these corner points of the pentagon that I mentioned earlier. And this is strictly bigger than if you just treat the other code word as noise in the second step, as we did before. Okay, so that's called successive cancellation decoding. Okay? All right. Okay, now we can repeat the same successive cancellation decoding in the other direction, and we can show that this other corner point is achievable. Okay, so we can do that. Now, can we do better than this? And the answer is yes, you can do better than this by decoding, instead of sequentially decoding recovering the messages, you recover them simultaneously. And this is what we call simultaneous decoding. So the idea is that you find a unique pair together such that x1, m1 hat, x2, m2 hat, and y are jointly typical. And with this rule, you can achieve the whole pentagon R of x1, x2. Now, you can also show, without for the Mac, performing the maximum likelihood decoding analysis is pretty difficult, but you can still show that you can still prove a converse for point-to-point codes, which is an extension of the converse that I mentioned earlier. Given P of x1, P of x2, and a decoding rule, if the limit on the expected probability of error goes to 0, then R1 and R2 must be in this pentagon region. So that means that simultaneous decoding achieves the same rates as maximum likelihood decoding. Okay. So the upshot is random point-to-point codes perform extremely well over the Mac, or can perform extremely well over the Mac. Every region R of x1, x2 can be achieved using random point-to-point codes, but you need to use a fairly complicated decoder. You cannot use your current point-to-point decoder. You need simultaneous decoding. And then the rest of the region can be achieved using time sharing between different random point-to-point codes. So this is the story for the Mac, is that point-to-point codes are great. Not only that, the results generalize to more than 2 senders. So we can actually have, so point-to-point codes are totally sufficient for that. So now let's look at the second network model, which is the interference channel. 2 sender, 2 receiver interference channel. Here, sender 1 wants to send a message to receiver 1, and sender 2 wants to send a message to receiver 2. And they are both communicating over a shared medium. So this could be, for example, 2 base stations communicating with 2 handsets over the same frequency band. This model was first studied by Al-Zuwaida in 1974. Now we can define the capacity region for this model in exactly the same way as before, as for the Mac. And it's not known in general. So unlike the Mac, we don't know what the capacity region for this model is. It's still an open. It's one of the key open problems in network information theory. However, we have some coding schemes that are optimal in some cases. Okay, so now again, let's look at how well point-to-point codes perform over the interference channel. Okay, so how do we use point-to-point codes over interference channel? It's pretty simple. You fix P of x1, P of x2, as we did for the Mac, and you generate a random point-to-point code for each sender. And again, you transmit the corresponding code words when you want to send M1 and M2. So that's exactly the same as we did for the Mac. Now let's look at decoding. Okay, so we can try, first let's try the decoding schemes that we use for the Mac. What did we use for the Mac? So now we have 2 receivers, so we are going to focus on receiver 1, and we can do the same thing for receiver 2. So for receiver 1, we can treat the interference from the other sender as noise, and we can achieve any point in this shaded region here. Anything less than I of x1, y1 can be achieved. On the other extreme, we can use simultaneous decoding. The receiver 1 decodes both messages, even though he's not really interested in the other message, in which case we get the pentagon, which is R of x1, x2 region that we saw in the case of the Mac. Okay, so first, it's not difficult to see that neither scheme uniformly outperforms the other. When you treat interference as noise, receiver 1 actually knows the code book for M2, and if the rate of M2 is not too high, it may be actually better to recover M2 and achieve higher rate. So you can achieve a rate higher by using this scheme. But then you decide to use this scheme, you cut down your rate for no reason. Okay. On the other hand, receiver 1 doesn't really want to recover M2. He doesn't have any interest in M2 whatsoever. All he wants to recover is its message. And so insisting on recovering M2 when R2 is high artificially limits R1. So you may be able to recover R2 maybe here, and if you use treat interference as noise, you can recover it. It's here, you cannot even recover it. Okay, so neither one of these two schemes uniformly outperforms the other. Okay, but we can get the best of both worlds using a scheme which kind of combines these two schemes in some form, which we call simultaneous non-unique decoding. The idea here is this. Receiver 1 finds a unique message M1 such that X1 M1 hat, X2 M2, and Y1 are jointly typical for some M2. As long as there is some M2, I'm OK. It could be multiple. I don't care, right? So I'm doing simultaneous decoding, but I am not penalizing you for not decoding M2 correctly. I'm saying fine, that's fine. Okay. Now, it's not difficult to show that if R1 and R2 is achievable using simultaneous decoding, then it's achievable using simultaneous non-unique decoding. That's really very straightforward. Less obvious, but true, is that if the pair R1 and R2 is achievable by treating interference as noise, then it's also achievable using simultaneous non-unique decoding. Okay? So the conclusion then is that simultaneous non-unique decoding achieves the union of these two regions. So it achieves this shaded red region here. Now, we can repeat the same analysis for receiver 2, and we get this R2 region. This is for receiver 1, this is for receiver 2. And Bendemeer and Kim and I recently showed that the optimum achievable rate region with random point-to-point codes, P of X1, P of X2, is actually the intersection of these two regions. So you can never do any better than this. What this says is that simultaneous non-unique decoding cannot achieve more than the union of simultaneous decoding and treating interference as noise. It just cannot do better. And simultaneous non-unique decoding achieves the exact same rates as MLD, even though I don't know how to analyze MLD. Okay? Okay, so this region is interesting. It's optimum when the interference is strong. It generalizes the result for the deterministic interference channel by Bendemeer and I in 2011. And it also generalizes the result for the Gaussian interference channel by Betchelli, Shea, and myself. So it's an interesting result. Can we do still better using point-to-point codes on the interference channel? And the answer is yes. But we have to add one more trick. What do? We use the Han-Kobayashi coding scheme, which, as I will show, is actually a coding scheme that uses point-to-point codes, even though it doesn't look that way. So the idea is, for the Han-Kobayashi scheme, is to decode part of the interference and treat each receiver codes part of the interference and treats the rest of the interference as noise. So what you do is you split each message into two parts, a public message and a private message. And then you use superposition encoding, which is a scheme that was introduced by Tom in his 1972 paper on the broadcast channel. What we do is we fix probability mass functions on these auxiliary random variables U1, U2, V1, V2. And we have two functions, x1 of U1, V1, and x2 of U2, V2. So what's going on here? What's going on is that we're going to generate four point-to-point codes. The U's will be the codes for the public messages that are decoded by both receivers. And the V's will be used to generate point-to-point codes that will be decoded by, be recovered by the, that will encode the private messages, as I'm showing here. So we have now 4 point-to-point codes used. But they're still random point-to-point codes. And now what do we do? To do the encoding, we cannot transmit U1, V1, U2, V2. These things don't exist in reality. What we do is we use the functions that we fixed up here to basically do symbol by symbol from U1v1 to X1 and from U2v2 to X2 symbol by symbol. And that's how we generate the transmissions. Now, one thing that the reason why this is called superposition coding is, for example, if the channel is Gaussian, you may want to use addition here. So basically what this is, you can think of this as saying, I'm going to have 4 different point-to-point codes, and when I want to transmit the message M1, I split it into 2 parts. One part would be the private message, one part would be the public message, and then I will pass them through this function, or I add them up together, if you will, and send the result. Okay? But I'm still pretty much using point-to-point codes. Okay, so now what about decoding? Well, it turned out that, again, in the same paper that I mentioned before, we showed that simultaneous non-unique decoding is actually rate optimal for this case. Okay, so to summarize, for the interference channel, random point-to-point codes plus superposition plus simultaneous non-unique decoding achieve the Han-Kobayashi bound. And the simultaneous non-unique decoding achieves the same rate as maximum likelihood. And we don't know how to do better than Han-Kobayashi, which means we don't know how to do better than using point-to-point codes. So that's very, very interesting. So for the MAC, point-to-point codes do everything. For interference, point-to-point codes do all we know. We don't know how to do better. So now let's talk about the third channel model, which is broadcast channel. This is a model like, say, an uplink of a downlink of a cellular system. We have 1 sender and 2 receivers. And we're going to consider the case when the sender has 2 messages, 1 for each receiver. This model was first studied by Cover in 1972. So now again, we can define the capacity region as the set of achievable rates R1, R2. And again, there is a trade-off between the rates because they are sharing the same broadcasting medium. So we don't know the capacity region again, just like in the interference channel case. We also don't know the capacity region for the broadcast channel case. But we know some coding schemes that are optimum in some cases. Okay? So here is one scheme that uses point-to-point codes and superposition. So we fix P of U1, P of U2, these auxiliary random variables that are going to be used to generate code books for the messages M1 and M2, and a function X of U1, U2. And again, we're going to generate the 2 point-to-point, random point-to-point codes for M1 and M2. And for encoding, we pass U1 and U2 through this per symbol function. Okay, so it's exactly the same as the scheme that we use for the Han-Kobayashi. Okay, now, if you look at this very cool animation here, just look at this. This is a broadcast channel, but I actually turned it into an interference channel in which each message is encoded independently of the other message, even though it is at the same sender. Okay? So what does that say? This says that this setting is exactly the same as the scheme I described for the interference channel without superposition. And all you do is you just replace the X's with U's. You get exactly the same scheme that we talked about. That's not the Han-Kobayashi, that's the simpler scheme before Han-Kobayashi. Okay? All right, so it's not clear that we can do better than this using point-to-point codes. I don't believe we can. But now, of course, S&D is random, and we get the exact same picture as I did for the interference channel with point-to-point codes. The intersection of these 2 regions is optimum for the channel. And actually, this is interesting. It includes superposition coding region by Cover and Bergmans, which is optimal for degraded, less noisy, and more capable broadcast channels. And it also includes the Cover-Vandermeulen region for the broadcast channel, general broadcast channel. So it's an interesting region, and you cannot really do better than this using point-to-point codes. But we can do better using schemes that are not point-to-point codes. Okay? So what can we do? So the idea is this. Remember, I told you that when we did this coding scheme, we converted the broadcast channel into an interference channel in which each message is encoded separately, which doesn't make any sense because the sender has both messages, so they should be decoded jointly, encoded jointly. Okay, so what we do is, instead of fixing product probability mass function U1 and U2, we fix a joint probability mass function U1 and U2. Okay? And then, of course, a function from U1 and U2 to X, as before. Now, how do we generate correlated code words out of independent messages? Right? That's what we're trying to do here. Remember, the messages are independent of each other, but we want to generate code words that are actually correlated. So the way to do this is using the scheme by Martin. And the idea is this. First, you generate a very large code book for each message. That's way bigger than the actual number of messages. Way bigger than the number of messages. And then you divide each random point-to-point code into subcodes, one for each message. So now for message M1, I have many choices of code words that I can send that would represent M1. And I do the same thing on the other side. Again, for every message M2, I have many, many, many options that I can use. Okay? Now, when I want to send M1 and M2, what do? I look in the bin for M1, and I look in the subcode for M1 and the subcode for M2, and find a code word on this side and a code word on this side that are jointly typical with respect to U1, U2. And this is the code word that would represent the two messages. So notice the code words are statistically correlated, but the messages are independent of each other. Okay? And then I send, as before, I send a function of U1 and U2. But what's interesting about this is that this is definitely not a point-to-point. If you look at the code book are the set of black dots here, one per product subcode books. And this is definitely not a point-to-point code anymore. So, okay. So to summarize where we are at, for the multiple access channel, random point-to-point codes achieve capacity region. For the interference channel, random point-to-point codes achieve the best known inner bound. But for the broadcast channel, we can do better than using point-to-point codes using, for example, Martin coding. So this is the first time we see that it pays off to do something other than our random point-to-point codes. So up to this point, I've been talking about single hop networks in which every node is either a sender or a receiver. So from this point on, I'm going to talk a little bit about multi-hop networks, where some nodes can be both a sender and a receiver. The simplest example of a multi-hop network is the relay channel, in which a sender wants to send 1 of 2 to the NR messages to the receiver Y3 with the help of the relay. And this channel model, so for example, you can think of this as communication between two base stations using a wireless channel and a satellite channel, for example. Okay, so this model was introduced by Vandermeulen in 1971. The capacity, which is the highest rate of transmission from the sender to the receiver with the help of the relay, is not known in general. But there are coding schemes that are optimum in some cases. So let me talk about that. Now what we are interested in again is how do networks perform when we only use random point-to-point codes. So the first scheme that we're going to look at is multi-hop. This is like your grandfather communication system. So we're going to send B-1 messages over B in transmission blocks. And for every block, we're going to generate 2 point-to-point codes, one for the sender and one for the relay. Okay. Now, during block J, the sender sends the code word for message MJ, and the relay sends the code word for the previous message which he recovered last time. And at the end of block J, the relay decodes the message sent in block J using joint typicality decoding, and the receiver decodes the previous message sent by the relay, considering the code word for the current message as noise. Even though he's interested in the message, he considers it as noise. This is what we do today. Okay? So with that scheme, it's not hard to see that you achieve the minimum of the capacity of this link and the capacity of this link, or the mutual information. It's not really the capacity, but I'm using that loosely. Okay, so this scheme actually can be optimum if there is no direct link, as you would expect. But it's not optimum in general, and we can do better using superposition and more sophisticated decoding. So we can, using random point-to-point codes and superposition and more sophisticated decoding, we can achieve the decode forward bound. So basically, the sender in this scheme knows what the relay knows, so they can coherently cooperate using superposition at the sender. So the way superposition at the sender works is you represent the message at the relay by a random point-to-point code using x2, and then so that would represent the message for mj minus 1. And then for the message mj, you generate a random point-to-point code using u, and then you have a function x1 from u and x2 as before for superposition. And you also have to use a sophisticated decoder. You cannot just decode each time. This time you have to use backward decoding. So when you do that, then you can actually achieve something better than multi-hop. It will be the minimum of this, the mutual information between x1 and y2, given that I know x2, and the rate from x1 and x2 as if they were sitting together sending information to the receiver y3. And this scheme is optimum for physically degraded relay channel. The decode forward doesn't do well, however, as you can expect, when the channel from x1 to y2 is not very good relative to the channel from x1 to y3, because then the rate is restricted by the rate to send the message to the relay. Okay, so can we do better? And the answer is yes, we can do better by relaying compressed versions instead of decoding y2 as in decode and forward. We compress it, or we quantize it, if you will, and send that. The relay just relays the compressed version. So again, this scheme does not really use point-to-point codes as we define them. So this scheme is a little bit different from it's not quite point-to-point codes, but it's actually pretty good. It's optimum for some relay channel classes. Okay, so to summarize, so for the relay channel, random point-to-point codes plus superposition plus backward decoding achieve the decode forward bound. But sometimes we do better with schemes that are beyond point-to-point codes, like, for example, compress forward. So now let's see what we can say about networks in general. First, let's consider the multicast network in which, with n nodes, in which node 1 wants to send a message to a subset of the other nodes. And the relay channel, of course, is a very simple special case of this network. So for this network, we can the code forward can be extended, albeit for a bit of a hacky way, and compress forward can be extended in a very nice way actually, and yields the scheme called noisy network coding by Young-Han Kim and myself. So how do these compare? One way to look at the comparison is to look at Gaussian multicast networks. So if we look at this channel, network as a Gaussian network, then we see that compress forward achieves within 0.63 n bits of capacity. That's not necessarily something wonderful when n is large, but at least there is a universal bound between what we can achieve and the capacity. On the other hand, you can show that decode forward can have unbounded gap to capacity. And so, in a sense, using point-to-point codes here can be pretty bad. Okay? In a sense. Okay, so now what about the story for multi-message networks? So in this setting, each node in the network has a message and wants to send it to a subset of the other nodes. And we don't have any general capacity gap result. We don't know of any scheme that has a guaranteed capacity gap result for the Gaussian multi-message network, or any other for that matter. So we still want to know how well point-to-point codes perform. How do we do that? Well, one way to do it would be to use the capacity scaling laws approach by Gupta and Kumar. What you do here is you consider 2n nodes randomly distributed in a unit area. Okay, so you throw these nodes in a unit area, and then you pair them up by pairing node j from 1 to n to node k j plus n. Okay, you pair them up. So we're going to look at multi-unicast situation. And we're going to assume a Gaussian network model with path loss exponent nu bigger than or equal to 2, an average power constraint. We ask ourselves, we don't know obviously what the optimum symmetric rate is. We have no idea what that is. But we can ask the question, what's the scaling law for this rate? So we can show that point-to-point codes plus cellular time division plus multi-hop achieve basically 1 over square root of n, basically a lower bound of 1 over square root of n, order 1 over square root of n. And we have an upper bound, which is n to the 1 minus 1/2 plus 1 over nu, where nu is the exponent, the path loss exponent, which is bigger than 2, log n. So there is a gap between the lower bound and the upper bound. Okay, so now to summarize, we've seen that random point-to-point codes with sophisticated decoding can perform extremely well. They achieve the capacity region of the multiple access channel. They achieve the Han-Kobayashi bound for the interference channel, which is the best known bound. They achieve the superposition coding and Cover-Vandermeulen bounds for the broadcast channel. They achieve the decode forward bound for the multicast network. And they achieve close to optimum scaling law for random multi-unicast networks. So that's the good news, except that we need to have to use more sophisticated decoding than we for point-to-point channels. We also found that joint typicality-based decoding does as well as maximum likelihood decoding in all the examples that I gave. We found that there are scenarios in which we need new network codes, Martin coding for the broadcast channel, and compress forward or noisy network coding for the relay or networks. And these network codes employ kind of lossy compressions and structure codes. So they involve something more complicated than simple point-to-point codes. So what does all this say about practical coding and communication? Well, it says that we should work on constructing better decoders, and it says that we should try to find better practical codes for broadcasting and relay. Okay? But an even better answer to this question, to quote Tom Cover, is that theory is the first term in the Taylor series expansion of practice. And thank you very much.
Tom, are there any questions?
Yeah, that's okay.
Any questions?
Very quiet people here.
We have a microphone. It's calling out for somebody to use it. How about you, Alon?
What?
It's an obligatory question.
Yeah, obligatory question. Implanted.
No, okay, so do we have a chance of, if we go away from point-to-point codes, of getting any approximate capacity for some of those networks? So.
Well, in the only example that comes close to what you're saying is the noisy network coding, right, for the multicast network. And that you can have kind of an approximation thing. I mean, it's not great, but for smaller networks, you can actually get very good bounds and so on. So the answer is maybe. Right.
How about the complexity of these new codes that we should look for? What is the status?
Well, right now they're terrible, right? I mean, right now they're just in information theory, right? So they haven't really. Well, I don't know. Maybe some of. I mean, some of you here who are more proficient in coding can answer this question better than I can. But I don't think they're anywhere near practical at this point. But on the other hand, I mean, the first thing is to take the point-to-point codes and do a better job in decoding. That you can give, I mean, you can just envision taking the current wireless communication systems and just improving the decoder, and you should be able to do better, right? So that to me is a low-hanging fruit, actually. But designing new codes may take time. I mean, I don't know.
Anybody else? I was just wondering, do you think that there may be other interesting network models that may arise, as our technology, is progressing so rapidly? Do you know of any people thinking about, not that these fundamental models aren't interesting and still pose a challenge, but maybe there's something out there that
you mean,
really requires something radically different?
Well, quantum channels, of course, is one example of that. I don't know of other examples, but that's the one that comes to mind. And that's the one that we'll be looking into the future, right? And that's definitely not represented. This is classical channels. So the problems there tend to be very difficult. I mean, but it's definitely something that would be interesting to see how well it will develop. What is this? What? What is he doing there?
It's a secret. Okay, if there are no other questions, let's thank our speaker for a beautiful talk.
What is this? Really?
Yeah.
Was he listening?
No, he's he'll have a few things to say.
Oh, okay.
So, one of the things you get is a beautiful poster.
Oh, okay.
It's replica of what's
Thank you very
inside.
much.
So his picture's already up on the wall in the center, so if you didn't go to the reception, you should go over and take a look at it. So. Thanks again, Tom.
Thank you.
Okay, there's one other thing that we typically do in connection with the Shannon Memorial Lecture, and that is we announce the recipient of the Shannon Memorial Fellowship. Sometimes we call it the Shannon Graduate Fellowship. This is another award that was endowed by Jack Wolf, and it's intended to recognize a student here at UCSD who's doing outstanding work in the area of information theory. And I have the pleasure of making the announcement right now. And the winner is here in the audience, luckily. It's Lily Wang. Lily, would you like to come up? So, Lily, congratulations.
Thank you.
It's a great honor. I'm glad you're surprised. There's a certificate for you right here. And this is an IOU for a substantial award. And I was going to say a few words, but we have somebody who knows your work even better. So this is Professor Young-Han Kim, who is Lily's advisor. And he's going to say several nice things about Lily. Okay.
Hello,
Hi, Young-Han.
so you can see me. Hi. So I'm very delighted and grateful that Lily received prestigious Shannon Graduate Fellowship. Is there a lot of echo here?
It sounds pretty good on this end.
Oh, okay, right. So Lily is originally from Guilin in Guangxi province in China, and she was the top student in the province, and she went to Tsinghua University even without taking the exam. And there, she was also admitted to the academic talent program in math and physics, which is the cream of the crop in the best university in China. And thanks to several right turns of events, we managed to bring her to UCSD, and which was over MIT in 2009. And probably in the future, some people may say that the rest is history. And indeed, the rest is history. She worked on a variety of problems in information theory, coding theory, communication, such as optimal relaying, broadcasting, interference management, coding for non-volatile memories, network coding, polar coding, and perhaps most importantly, lots of mathematical puzzles. And every week during my seminars, she brought exciting and very interesting puzzles and tried to convince us that we should work on them. But the most amazing thing about Lily is her extremely high energy. There are many anecdotes that shows how serious and enthusiastic she is about potential learning opportunities. And let me just share with you just one. When she was unofficially TAing for my course on network information theory, she was in charge of preparing the weekly homework solutions. And every week, she brought me near-perfect solutions. And so I thought, okay, she's great. But later, I learned that she spent more than 20 hours per week preparing the solutions. And all the while, she was taking 3 courses. So all in all, Lily is bright, hardworking, and probably one of the best students I ever had. I dare to say she deserves every bit of this prestigious award. Congratulations, Lily, and thank you very much.
I didn't prepare anything, but I want to thank Young-Han and everybody here for sharing this exciting moment with me. I would like to thank everybody, especially Young-Han for giving me the chance to doing research in network information theory and many exciting problems. It's really hard to express how much I want to thank Young-Han and he opened the door for me and led me to this exciting area. And yeah, everything I want to say is thank you very much, and I will keep on working hard. Thank you.
Is the photographer still in the house? It would be great to get a picture of Lily with her advisor who's in South Korea. No? How about somebody have an iPhone? Can you get them both? It's kind of hard to miss Young-han.
Should I smile?
Sure. We shall share the award with you. Okay, thanks. I do want to mention one more thing about Lily that I think is really indicative of her capabilities. She and one of my students, Minghai Chin, were one of the recipients of the Qualcomm Innovation Fellowship, which is a $100,000 award that they got for their proposal having to do with the application of polar codes to network communication. And if I remember the numbers correctly, I think only, was it 6 or 8? There were 8 out of 133 submissions that were chosen for this. So it was really a hard-won award, and I think it's a testament to her talent that we can be proud of getting one of those things here at UCSD. So congratulations again, Lily. Okay. Thank you very much, Young-han. I know it's about 9:15, so you should get to work.
Yep. I'm at a local conference.
Okay. Okay. Thanks again for Skyping in.
Thank you. Bye, everybody. Bye, Abbas.
Bye-bye. Okay. Well, that's it, folks. Thank you all for coming. And thank you again to Abbas for a beautiful presentation. And we hope to see you next year. Actually, that's quite what you were saying is quite relevant to what Lily and